All right, very good. So this second semester, we have assumed that you have progressed through the standard sort of skill building that we did last semester with electronics and programming, et cetera. So this semester, we're going to be focusing on using that knowledge to work as a team and develop a flight payload. So I'm going to talk to you a little bit about what it is that we're going to be doing this semester. So the objectives for this semester is really twofold. We're going to work with you as teams and help you use the knowledge that you gained last semester to create a science payload. The other thing that we're going to emphasize much more this this semester is communication, and you're going to be going through a series of required documents that we are going to review, and you will use to communicate to us how you're doing with the payload. Some of these documents, as you go through in previous groups, previous teams, it's not unusual for a student team to end up with a final document that's close to 100 pages long. But don't be too scared yet. We'll gradually build that up as we go through this semester. Finally, if all goes well, we will conduct a flight in May with these things and have all you folks participate. But obviously with the issues with COVID, we're going to have to watch that carefully. So a lot of this depends upon how well the vaccine gets distributed and how well things open up. So this is going to be a dynamic decision. Okay, so the things that we're going to be doing this semester is that we've got one more piece of hardware that you folks are going to have to construct, and that's the Megasat. That, along with the Arduino Mega and the Adafruit GPS SD card, is going to form the core of your payload, and then you can add on to that for different kinds of sensors. We're going to insist that you start working as a team. Your faculty advisors are going to guide you with that. One of the exercises that you'll probably need to do is the development of a team contract. We'll talk about that. The emphasis here, at least for the next couple of weeks, is going to be on project management, how project management works, and the kinds of things that you do when you're trying to manage a project. Then you're going to be getting into things like the design reviews as you develop your payload. So a preliminary design review, critical design review, and a flight readiness review at the end. Again, if things go well, we'll be doing a thermal vac test of your payload in sort of middle towards end of April. So and then flight in May. So that's sort of where we're going. All right, so here's so we talk about in management, we talk about requirements. So here's your first set of requirements. These are the requirements which are going to be on your payload. Your payload will not weigh more than 500 grams. It is limited to 500 grams. It is going to be roughly a prism with 15 or 20 centimeter long sides, basically constructed out of polystyrene foam. And another hard requirement, those two in the size and the foam are not necessarily hard requirements, but this one is. Your payload must be constructed so that two strings can pass completely through the interior of the payload, and those two strings are 17 centimeters apart. That's so that you can attach to the flight stream. You're going to have to conduct some sort of science or engineering or technology. You're going to have to prove that your payload is space worthy and go through those three design reviews. Once you fly, 48 hours after that flight, your team is going to have calibrated science results and you're going to have to make a presentation on your results to NASA, to a group of NASA professional scientists and engineers. So you need to come into the flight in May ready with your ground software, your fully functional flight payload, etc. Okay, so the Megasat. So you're going to be starting to work on that one in a couple of weeks or so. The Megasat is shown here. You're already familiar with the Mega, and you're also familiar with the Adafruit GPS. And so what's in between here is a custom designed board that we built here at LSU. It has a collection of sensors already on it: 2 temperature sensors, a humidity sensor, pressure sensor, a 3-axis accelerometer, a 3-axis gyroscope, and a real-time clock with a battery backup. So this combination of the Mega and the Adafruit GPS and the Megasat is a core payload that gives you sort of environmental information and allows you to record data while you're flying. There are prototype areas on the Adafruit GPS. If you want to add additional circuitry for other kinds of sensors, you can certainly do so. You can also get prototype shields that will just fit within this stack format that you can also use for interfacing. So this is the core. So this board, you'll be going through a couple weeks about the surface mount soldering techniques that's used on this one, and how to build it and construct it. So your faculty advisor will come up with different kinds of options for different kinds of payloads. So here's a couple of examples about what you might do with this system and expand it. You can look at background radiation as a function of altitude. You can measure the bands of UV, again, as a function of altitude. That UV is the intensity of UV, particularly the UVC band, is very sensitive to the position and properties of the ozone layer. So that's sort of an indirect way in which you could measure the ozone layer. You can measure concentrations of other gases, carbon dioxide or carbon monoxide or nitric oxide, a variety of other things like that. You can develop a system for measuring airflow. When you start going to lower pressures, this becomes very difficult. And so that's a really interesting kind of experiment as to how you would measure airflow in the absence of air on that. You can also look at methods to optimize atmospheric temperature, how you actually do it. It's a non-trivial operation if you really think about it, because if you have a sensor and it's dangling out there, what are you actually measuring? You have space, which is above you, which is at 4 degrees Kelvin, and you have the Earth below you, which is at 273 degrees Kelvin. So what's the air temperature? All right, and it also depends upon what color that you make your sensor. White or black will give you 2 different temperature readings. So how do you actually measure air temperature while you're in a flight? So that's another non-trivial operation. Thermal flow and conductivity, the boundary layer around the payload, that's another interesting one. You can also look at a inertial sensing system. You've got an accelerometer and a gyroscope and a GPS unit. You can use that to possibly figure out what your orientation is as a function of time, and maybe determine whether you've got a sensor that could look at the sun on this. Now, one thing to keep in mind, since I just mentioned that, is that in late 2023, there's an annular eclipse across the United States, and in April 2024, there is a total eclipse. These are the 2 paths of these things. We will, or LaSpace will, be holding a competition, as we did for the 2017 solar eclipse, to pick a subset of affiliates and student teams to actually go with us to the solar eclipse and fly balloon payloads. So it behooves you to take a look at kinds of payloads that might be useful during a solar eclipse. What would you actually measure during a solar eclipse? So those are things to think about as to how you're going to proceed with your payload design. Now, one of the things that's really critical, which makes or breaks a team, is how cohesive your team is, and part of that is, have you actually thought about and written down your rules of engagement? In other words, what's your meeting schedule? How often do you meet? How do you keep track of your versions? How do you assign tasks? How do you verify that those tasks are completed? What happens if one team member doesn't complete a task? What happens with that team member, but also what happens to the task? So there's a whole bunch of things that you need to think of in terms of operating as a team for what your rules of engagement, how you're going to operate as a team. Your faculty advisor will lead in this effort. We do not need to see your team contract, but you should put it together and write it down, because that is probably about the only time that you're going to have in order to figure out how you're going to function. All right, and my last bullet on here is 100% true. All right, teams, and we've seen this over the last 15, 16, 20 years that I've been doing this thing. Those teams who do not spend sufficient times communicating and writing things down in terms of how they operate have a much higher probability of failure. So it behooves you to sit down and spend this time. All right. So for the next few days, we'll be going through our next few sessions. We'll be going through a variety of lectures. Most of these are already on the ACES course site. And as we go through, if I modify anything, then we will update those as we go. And obviously, I'm doing video recording now, and so those video recordings will be on the website as well. So this gives you an idea about the kinds of things that we'll be discussing in project management. Also included this semester, as we go through this, are going to be things like mechanical guidelines and constructing the megasat, and how you put together a structure out of the styrofoam, power systems, et cetera, et cetera. So those will be conducted also. However, a lot of the semester is going to be self-directed. You're going to have to put together your own documents and develop your own teams, and so that's nothing that we are going to lecture you about. Maybe your faculty advisor will lecture you about it, but we won't. However, there are 3 documents that we are going to require, and that is the preliminary design review, the critical design review, and the flight readiness review documents. We are not going to require presentations of these, except for the FRR just prior to flight. But your faculty advisor may require you to do presentations of these things too. We have constructed a series of templates, and we'll get into that in a second. And those templates are designed to guide you through the content of these documents. So we suggest that you pay attention to them. Each one of these reviews has slightly different emphasis, and it allows us to check on your progress. You should note that these documents were getting very serious. You know, the documents that you put together last semester, we sort of use those as an exercise and to see how you're doing. But these documents this semester are going to be much more serious. They are going to determine whether or not you actually do fly. All right. So take it seriously. Make certain you put the time in to do that. So here's there are 5 templates on this, pre-PDR, PDR, pre-CDR, and that CDR, it's critical design review, that actually should be CDR in there. But these are templates. They are on the LaACES Document Center. You can take a look at these templates, and I would advise you to look at them early rather than what they build upon each other. If you do not complete one step, then you're going to be behind. All right. So pay attention to what they are. Now, the next lecture, I'll be talking a little bit more detail about what the expectations are for each one of these things. All right, here's the schedule. All right. So there are internal deadlines in your institution about a variety of things. We suggest that at least your first version of your team contract be completed by January 28th. And we suggest that your pre-PDR, again, determined in your institution, be done by February 1st. We want to see your document, PDR document, by February 22nd on this. Likewise, the CDR document, March 31st. Currently, we're planning the thermal vac test of April 16th. I believe that's a Friday. And then your FRR document is due May 3rd. So it may seem that there's a lot of time between now and May 3rd, but it isn't. So you need to hop onto these things and get these things serious. So that's the end of this first lecture.